So thanks for everyone for coming. It's a really busy time in the quarter. Everyone's busy with the homework project and midterms. Today I'm gonna tell you something I'm really passionate about is the speech-brain-computer interface. My research, before that, I'm just some self-introduction. So I'm Chaofei. I'm from the Stanford NPTL lab. Our lab trying to build brain-computer interfaces to help people restore communication or restore movements. So today, I think I'm just gonna really tell you guys how cool this brain-computer interface is, given that we have so many recent development in the AI and the machine learning. And I hope you guys can enjoy this talk. All right, so let me first start with a video to give you some motivations why we want to build a brain-computer interface. Yeah, I think what the story tells is that we saw this teenager, Howard, who's 21 at the time of this video, was shot. And he lost all his dreams because of a severe stroke that also made him in this kind of a lock-in state where he can't move. And he talked about he used to going out and play football, making friends, and just let his emotion out. I think all of this is lost to him, and I think the most important thing is that he couldn't really speak to express himself, to let all the emotions out. So Howard is just one of those individuals who suffer from this kind of neurological disorders such as brainstem stroke or ALS that can cause severe speech and motor impairment and even complete loss of speech. These individuals, I think the life is really challenging for them, right? Just think about it. You cannot speak, you cannot move. You still have a fully functioning brain, but everything is lost. All your dreams could be shattered. So I think for people like Howard, as you just saw in this video, the way they can still communicate with the outside world, with their loved one, is through this assistive communication devices, such as the one we just saw in the video, which is this kind of letter board that has letters organized physically. And for people like Howard, which may still have some residual eye movement, they can use their gaze to tell his friend where he's looking at, and then his friend can use the gaze to tell what letter he's trying to say. Just imagine how slow this process is if you want to just say a sentence. It might take you a few minutes to express simple things like how are you, I'm feeling not comfortable today. An alternative here is you can also use a eye tracking device so that people can use eye trackings to type on the computer on virtual keyboard. But by just think about if you have to look at the computer screen all the times, all day, it's really tiring for them. And also these people are not like us. They probably, even if they still have a residual eye movement, it's very hard for them to move their eyes. So it's very tiring as well. Maybe something different here is that maybe some of you guys have already seen this recently. Is some videos published by a company called Neuralink. For example, here's one video here. Let me see if I can play them. Hopefully I can play them. All right, so I think here is that this company Neuralink is developing this kind of a tiny implantable device that can be actually placed inside your skull and then read the brain signals. The hope here is that because for people like Howard, their brain is still fully functioning. So the hope here is that maybe we can using this kind of a direct interface with their brain so that they can still use their intact brain to control a computer or even robots to help them to live a normal life. And here is a quote from their participants, Nolan, and he's pretty excited about being able to using this very state-of-art BCI to be able to connect with their families and then be able to support himself. I think this kind of like BCI, what am I trying to say here is that for people like Howard or like a lot of people who has lost their control of their body and language, I think BCI can bring hope to them. So that's what I'm going to motivate here today, is that we're trying to use BCI to really help these people. But I think before going into the details about how this works, I just want to first go through a brief history of brain-computer interface, just to help you guys understand how this thing works, like why we can put such tiny devices into the brain and then suddenly can interpret what the brain is doing. Like, there's a lot of interesting stories here. So let me start with a brief history of BCI. So first, back to the 19th century here, a British scientist called Richard Caton started to do some experiments on animals. And one of the things he found is that you can actually measure the brain activity, like measure electricity from the brain. Moreover, if you ask the animal, not ask them, but like let the animals do some tasks, say moving their heads, then you can see that the electricity changes somehow. So I think this is the very first early experiments that scientists do to show that, okay, actually you can decode some signals from the brain, but we still don't know how exactly what those electric signals means here. So fast forward to 1924, a German scientist called Hans Berger invented this device called, I always forget how to read that word, but anyway, so it's short for EEG. So it's basically this kind of like on the right, you can see that's kind of like this electrodes that you can place on the outside of your, basically on your skull, and then measure this kind of like a wave, like signals. So what the scientist Hans Berger found is that First, he's the first scientist to find that you can actually measure this kind of like wave like signals from like just this kind of like electrodes placed on the head. And then he found that this kind of signals has very different say frequency depending on how the user, how the patient is the function, like the state of patient is. For example, if the patient is in this kind of very calm state, then you will have generate this kind of like a slow alpha wave around like 10 to maybe 20 hertz. I forgot the exact range. But if the patient is open their eyes and then doing some like a cognitive demanding task, then you'll see really sharp beta waves. So he's the first scientist to discover that you can actually, using this kind of like electrodes to measure the brain, the electric signal of the brain. And also there's a funny story here, is that Hans Berger used to be a soldier. And then one day he was training on the horse, and then he fell from the horse and suffered from a concussion. He also has like a twin sister, not a twin sister, but he has a twin sister. And then the story is that at the same day, her sister felt like there's something weird, and then he's just starting to worry about his brother. So his sister sent a telegraph to his father and telling his brother that is his brother okay. So this really intrigued Hans Berger that maybe there's something called a telepathy that can connect to people through this kind of like whatever this brain wave. So that's his motivations to start to study psychology and neuroscience and invent this EEG, which we are still using today to diagnose like things like epilepsy. Okay, and then people starting to using this kind of EEG devices to perform, like to use it to maybe things we can somehow detect this kind of wave like things from the brain, and then we can also control the frequency of the wave. So someone started, like a musician here, starting to use this EEG devices to perform music, right? Anyway, so I guess you guys already got the idea that someone is controlling, like trying to perform some music with his brain wave. I think this is a really cool experiment. It's done I think in the 1950s, and you can already see that people starting to get the idea that you can actually bypass like your body. You can actually use your brain, directly connect your brain to some like external device and controlling that device. So I think the idea here is that what if we can also leverage the same idea, but to help people with like Howard, you can help them to maybe control a robotic arm. But like the problem with this kind of like a EEG or external measuring device is that the signal you get is very weak. Just imagine that your brain is generating, we probably know that the brain has a lot of neurons, right? The neurons actually generating a lot of like signals. And if you just put some electrodes on the scalp, and then what you are actually measuring is like the average neuron firings of like maybe millions of neurons, which is, if you think about like analogy, is that if you are trying to hear what people are saying in the room next to us, but we can only trying to figure out like what they're saying in this room. What we are hearing is kind of the mumbling of a lot of things. We can probably just tell maybe they are in this kind of like a happy mood, or maybe they have reached a conclusion, but not exactly what they are trying to say. So the limitation here is that this kind of EEG device can only give us very low precision or like low resolution signal. We want to get better signal. So how? I think the answer is trying to go inside the brain and then putting this kind of electrodes next to a neuron and then trying to directly measure the neural activities of these neurons. And for the purpose of this talk, we're mostly going to focus on the neurons in this region of the brain called motor cortex. So this brain, as some of you may already know, that brain has different regions that's doing different tasks. So in the center of the brain, it's called motor cortex. It's basically controlling all your muscles, or all your body muscles. So the hope here is that if we can understand the neuron, the coding of like the information of the neuron that's encoded here, then perhaps we can decode this information and then use this information to help people like Howard to be able to control a external arm or be able to speak again. So here's some very basic neuroscience. So we know that there's this kind of cell called neurons, right? So each one of this thing is called a neuron, and this is the body of the neuron called soma, and then this is the axon. So this is another neuron. So a neuron connects through this tiny thing called synapse. So if neuron want to transfer some information to another neuron, just like in artificial neural network, you have some neurons and then you want to send information to the next layer, you can basically, this neuron will generate some action potential, which is just some like electricity here to signal that another neuron that there is some information there. So if you put a tiny electrodes, say, on the axon of this neuron here and measure the membrane potential, what you will get is something like this. So you will have like on the x-axis is the time, and on the y-axis is the measure the electric potential. And then you will see this kind of like a very sharp spikes. And then if you zoom into the spikes, you will see this kind of like a typical firing signature of the neuron, which is like the electric, like if the voltage suddenly goes up and then goes down. So basically what you can measure at the neuron is that it's kind of very sharp spikes. That's what you will get by putting electrodes next to a neuron. Okay, so how do we figure out what kind of information is encoded in this what called a spike train? We can perform some behavior tasks here. So for example, here, suppose I was still listening to a single neuron, and this neuron is, let's say we are using a monkey for this experiment, right? So we are training the monkey to do two things. One thing is basically we are trying to instruct the monkey to move his hands either to the left or to the right, and then we measure the firing or the spikes of that single neuron and then trying to get what kind of information is encoded by that neuron. So what you see here is that each row here is basically a spike train of that neuron. As you just saw here, each vertical line is just a spike of that neuron. Each row is a trial. A trial means that the monkey is just trying to move his hand in like one direction. Then the vertical, if you see here that, because like you can see here that the neuron seems to fire slightly different across trials. So I think that's the one like fundamental properties of a neuron is that it's very noisy. It's not like in an artificial neural network, if you put something in, you always get something out. Whereas in a real neural network, in a real neuron, things are really noisy. So sometimes they fire a little bit faster, but sometimes they fire a little bit slower under the same experimental conditions. And so here, what we are trying to measure is that what kind of information is this neuron encoding when the monkey has moved his limb to the left or limb to the right. And then when we can also split this information encoding into two phases. One is a preparation and the other is the execution. So for preparation, for execution means that the monkey is actually moving his arms, whereas the preparation means that the monkey is preparing to move, but he's holding his arm fixed. So he will actually move his arm at this this go time here. So what we can see here is that it seems like this neuron likes to firing a lot during the execution when the monkey's hand is moving to the right. And it also fires a little bit more when the monkey is preparing to move to the left. So this means that maybe the neuron is encoding some movement direction here. So basically, if you can repeat this experiments for many different neurons and for a lot of different directions, and eventually what scientists find is that the neurons, like if you fit, like say for a single neuron, if you fit the firing rates of that neuron, basically how many spikes it's generating every second, to different movement directions, you can fit this kind of like a cosine tuning curve to it. So what this tuning curve means that on the y-axis is the firing rate, and then on the horizontal axis is the movement direction. So this neuron prefers to like firing the most when the movement is say 180 degrees to some reference, and then the firing gradually goes down. So that's like the first thing scientists find, like how the like single neuron encoding like movement information. And then if you measure multiple neurons, like you will find that each neuron could encode very different information. For example, this green neuron here, its tuning curve is slightly shifted to the right, and then the magnitude is shifted down. So its preferred direction is around maybe 250. Now with two neurons, you can actually decode out more, actually decode out what the intended movement direction is. Right. So for example, with a single neuron, like suppose that right now I measure the firing rate is around like 30 spikes per second, then there could be two movement direction with 120 and then 240. However, with second neurons here, you can see that we can basically eliminate the, like suppose we measure the second neuron fires around like five spikes per second, then we can exactly pinpoint that actually the movement direction is 120 instead of the other one, right? However, we know that neurons has some noises, so we actually cannot really exactly tell the movement direction by using two neurons here. So for example, in the third plot here, right, due to the noise, the actual, like suppose the ground truth, like the actual fire rate is those gray lines, but due to the noise, the firing rate is slightly shift to those dashed lines. And you can see that originally, if we can decode the movement direction is 120, but in this case, the possibility becomes like there's 4 possibilities we cannot uniquely define. However, you can see that maybe it's still more likely that the direction that the monkey tries to move is like around 120 rather than the 1 to the left, which is like around 50, and then the other one is more like greater than 240, right? So how do we deal with this kind of like a noisy neuron? Like how can we still uniquely, like more accurately, like how can we still accurately decide decoding this intended movements from this kind of like a multiple neuron recordings? I think we can basically use machine learning here, right? So we can treat this as a kind of like a classification problem. So here we are plotting each dot here is basically a firing the combination of two neurons. And the color here basically represents the intended movement direction. And then if you like somehow train a machine learning classifier here, then you can basically see, we can draw some like decision boundaries where say on the right side, where those, if like on new measurement that we get that the firing rate somehow falls onto this here, then we probably know that it's going to be, the monkey is trying to move to the left direction, right? So I guess here, like, we know that, okay, we can do this kind of a single neural measurement. We can measure firing rates of multiple neurons. And then by training machine learning models, we can use this machine learning models with the neural data to infer like what's the likely movement directions. So this is how we are going to build up to actually build a brain-computer interface. Questions? Yeah.
For all of these data, you mentioned like neuron 1 as a very like specific number. How do you pinpoint which neuron can start measuring?
Yeah, so here neuron 1 is basically like we are taking, so we are here making an assumption that each tiny electrode here, you see, is measuring like exactly one neuron. And then that electrode will be fixed, always measuring the firing rates of that neurons. Yeah. But in the real case, it's not always the case, because like you think about it, the brain is this kind of like a soft structure. So if you put electrodes there, it could move a little bit and measure different neurons. So that's one of the challenging problems of BCI, is that how you can deal with this kind of like neural change, recording change, yeah. All right, let's go back to here. So now we can basically know that we can put some electrodes into the brain, into the motor cortex, measure some signals, and then we know how the neuron encodes those signals, and then we can also build a machine learning decoder to decode those signals, right? So we can basically have some like methods to be able to build a brain-computer interface so that we can interpret what the like a still functioning, fully functioning brain trying to do. One more thing is that, so how we can record this signals. So yeah, this is a very complicated figure, but don't worry about all the details. What I'm trying to show here that basically there's a lot of different technologies that you can use to record brain signals. But when you think about these technologies, you can think about it as in this kind of two-dimensional way. So on the y-axis is think about it as a spatial resolution. So the higher up you go on the y-axis, that means that you can basically measure like very it basically shows like what's the region, like what's the size of the region of the brain that you can measure. So if you go really high up there, then that means that you can only measure, say, a very large, like the average brain activities of a very large brain area. Whereas if you go down the y-axis, that means that you can actually measure to very fine-grained scales, like such as a single neurons. Whereas the horizontal axis here means like the temporal resolution. That means that for technologies such as this kind of like a single neuron recordings, you can basically measure like exactly at each time point. For example, like 1 millisecond, what's the like electric potential is for that single neuron. Whereas for recording technology such as MRI, which basically measures like the blood flow in a small brain region, you can only measure on average like around like say 0.5 seconds or 1 second, what's the blood flow changes in that small brain area. So that's really like average of a lot of information, because we know that the neuron fires like this really like fast speed, right? The firing, the electric potential change of a neuron is usually around order of 1 millisecond, right? So if you can only measure things around like say 1 second, you are basically like averaging, smoothing out a lot of informations. So ideally, we want to have something both have like a high spatial resolution and also temporal resolution here. So what we will use in most of this right now in a lot of like a clinical trial in our lab is this kind of like a multi-electrode arrays. So each electrode here is like a tiny needle that can measure maybe a signal of a few neurons, and then you put this needles into a small tiny like a square on the size of like a fingernail, and then you can measure maybe on the order of hundreds of neurons. All right, so now we can have this devices to measure neurons. Let's go into a more like examples of how we do this here. So here's let's take an example here. Suppose someone have a like say spinal cord injury and then lost the connection to his body. So his mind is still fully functioning. So the question here is that whether we can still, what kind of information we can still decode from his motor cortex such that we can decode those informations and then use those informations to either control his arm or like his own arm or like artificial arm. Right. What we're going to do is trying to put this kind of tiny electrodes, microelectrode arrays into his motor cortex, really penetrating into his like the surface of his motor cortex. And each electrode here, as you see here, is this kind of tiny needle, and those gray triangle is the size of a neuron. So each electrode maybe is measuring the firing potential of multiple, like local field potential of multiple neurons around it. And we can pass all this information in real time to a computer through this kind of like a wire right now. And then this is what we'll get on the computer here is that, for example, here each block is basically the measurement of that one electrodes. And if we do some like behavior experiments as we just showed now, we can probably figure out the tuning curve for each electrode. For example, this one is probably like its preferred direction is to the left. So we can repeat the experiments, behavior experiments for other channels here, and probably train a ML decoder to figure out what this channel, each channel is encoding, the preferred direction for each channel. So once we have the decoder trained, and then at test time, we can basically ask our participants who has the thing implanted in his brain to trying to imagine to move his hand to some directions. And then the decoder will trying to figure out the direction he's trying to move, right? So that's the basic idea here. Let me go to a demo here. So this is one of the research coming out of our lab in 2017. So here you see a participant is typing on a virtual keyboard with her mind, right? And then on the bottom shows the typing speed measured as the correct characters per minute. So it peaks around 40, and then on average maybe it's around like 20. I think this is really amazing. Like, think about like for people like Howard who used to have to using this kind of ladder board to communicate. Now, with this brain-computer interface, he can fully communicate by himself through, like say, a computer. So that's a huge improvement over ladder board. Yeah.
Does a person open the eye or close the eye?
He still opens his eyes. I mean, she still opens her eyes.
So is there anything with the eye tracking?
Not for this experiment.
So even she closed the eye, still work, right?
Yeah, it will still work, but like she won't have the visual feedback. You know, she won't know where she's typing.
But how about like if she came up with a character in the mind? without looking at the keyboard?
Okay, that's something I'm going to show next. So,
Okay.
yeah.
How do you know whether it's the person who mistyped or whether it's the machine that's not capturing the correct character? Like, I'm confused by what do you mean by correct here?
Okay. Oh, here. So yeah, that's a good question. So let me clarify here. I think the task here is maybe it's not readable, but I think the task here is basically she is copying a sentence. So there we know the ground truth, then we can measure like the error rate. And yeah.
I was going to ask, how do you capture like the clicking motion or the like selection motion? Is that easy to distinguish, or is there a certain way of knowing that the user is pressing down, or does she visualize like a mouse or actually clicking?
That's a really good question. So as I just mentioned, right, so we can decode movements, and we can also decode, like, say, different gestures, say, like say you can use this kind of gestures or like move her elbows. So you can just imagine different motor movements, and then we can basically decode those motor movements and map that to, say, a click signal or different signals.
So let's say if the person look at the keyboard and then remember the keyboard in her memory, and then she close the eye, and that's still work.
I think that's really even like that's even harder for me to do, right? I can't remember. Like, can you remember the keyboard and then just control, like, say, a mouse and?
I use the keyboard every day, so I definitely remember the word prediction in my mind, and then just close my eye.
But this is like a virtual keyboard, so it's not like a physical keyboard. We can use your muscle memories. So maybe one thing I have to clarify here is that the mental image for her is to, say, controlling like what's the word? I mean, it's just like controlling a mouse, right? So she's not actually doing the touch typing, but she is actually moving, like, say, a mouse. Right. Let's move on. All right, so this is basically just to showcase that building up on all the knowledge we have learned about the brain. So we can basically decode some attempted movements from people like this, I forgot her name, but like I think it's T6, that code name T6, that we can really help this kind of people to regain communication through this kind of BCI. And I think, as I mentioned earlier, you can also use BCI to control robotics arms. So for example, in this case, this is the participants in, I think, Caltech. Oops. He's using his mind to control this robotics arm, which grabs him a drink.
Cheers.
All right.
Hey, you finished that thing off. That's good. And that's how science is made. All right.
There you go. All right, so, and also you can do things like restore working abilities. I think as someone just mentioned right now, just now, is that maybe there's like, we can try to restore different modalities of communication. For example, just now we're just using the movements, and then by restoring movements, we can control computer. But like, how about we directly restore the abilities to do handwriting, right? Because handwriting is very natural ways to communicate. So Frank Willett, research scientist from our lab, in 2021 published a paper to show that you can actually do this kind of handwriting BCI, and he showed that it's actually really, really fast compared to the previous one. Okay, so now we have seen that there's different ways to restore communication. Here's just like a table, a measurement of different ways of communicating, right? You can see on the very left is say sip and puff interface is very slow. Basically, that means that for someone who can not really move but can still do some like a breathing, they can do this kind of like a sip and a puff to say yes and no to communicate. That's really slow, maybe around 5 words per minute. For a normal person, I'm really surprised that on average a normal person can write maybe 13 or 14 words per minute. That's really slow, but maybe that's just the average speed. And on the very far right side is the natural communication, which can reach up to 150 and 60 words per minute. Just put everything into context here. So the 2D cursor, I just show you guys right now, it can do 8 minutes per word per minute, 8 words per minute. And the handwriting can do around like 18 words per minute. So compared to the, say, letterboard or like this kind of eye tracking, we are doing, like, we are really make a lot of like advancement here, but still it's way far from like the natural conversation speed. So the next question basically is, okay, how can we get there? Can we actually restore can we actually restore speech with brain-computer interface? To get there, I think there's a huge barrier here. First is that the language processing in the brain is a really complicated process. So for example, here is showing all the brain areas that's involved in the language, and we still don't know exactly how this happens, but this is just our best guess at how language is processed in the brain. On the very right, you see that there's a lot of brain regions that's involved with knowledge and reasoning. In the center is maybe areas that's involved with semantics and syntax. And on the very left is about the perception of speech and then the production of speech. Language is really complex, so maybe the hope here is that we can start with motor cortex, with motor planning of language, because since I've just shown you guys that we already know how the motor cortex can encode movements, right? And we can also know that in order to produce language, we need to speak, and then maybe we can put some electrodes into this part of the motor cortex that actually controls our oral facial muscles, and then trying to decode some information there, then see if we can actually restore speech. To actually being able to restore speech is, I think it's more complicated compared to the restoring movements. So what I'm trying to say here is that the production of speech is really a lot of complicated movements, and it's really rapid. It's just more than just moving your hands to certain directions. So restoring speech is much harder than just decoding out those movements of each articulators. So instead of trying to decode the movements of each articulators, because it's very hard, right? So also like for people who has like Howard or people like has lost speech, it's very hard to actually measure their speech articulator movements. Instead, maybe we can try to decode out this kind of like a discrete phonemes instead of like this kind of continuous speech articulator movements, because we know that all the languages can be decomposed into this kind of the basic phonetic units. For example, for English, we know that there's different vowels and different consonants. They are correlated with how you place your tongues in your mouth and how you place your different speech articulators. So here we're trying to, instead of decoding the actual articulator movements, we're trying to decode this kind of like discrete phonemic tokens. And then there's a previous work showing that if you put some electrodes on the motor cortex, and then you can actually tell the differences by measuring the differences of different phonemes by measuring the electric activities in the motor cortex. So there's a hope of being able to restore speech by just putting electrodes in the motor cortex here. And indeed, so in 2021, researchers from UCSF actually demonstrated it's actually feasible to build this kind of like small vocabulary speech PCI with this ECOG recording technology. The difference between ECOG and then the microelectrode array I just showed you guys is that whereas the microelectrode array actually penetrates into the cortex, but the ECOG stays on the cortex, so it doesn't actually record single neuron firings, it still records some average neural activities over a small region. So compared to microelectrode arrays, they will have a slightly lower resolution. So that's why their prototype is around this kind of like a small vocabulary PCI, which can only decode 50 words at around maybe 75% accuracy. But this is still very exciting work that showcases that you can actually achieve this kind of like a speech decoding using by putting some electrodes into the motor cortex. All right, so I'll just right now go into the research that's done in our lab, which is to build a high-performance speech neuroprosthesis. So in 2022, so we recruited a participant codenamed T12 who has ALS. So T12, she used to be a very active person. She likes to ride horse, likes to jog, but because of ALS a couple of years ago, she basically couldn't do all those things that she used to enjoy. And unlike most ALS patients, her symptoms starts with the orofacial movements first. So she still can move her hands a little bit, but she cannot really speak intelligibly. So we decided to put 4 microelectrode arrays into her brain, 2 arrays into her motor cortex, and then 2 arrays into the part of the Broca's area, which is supposed to involve with language planning. So the hope here is that we want to both decode the execution of speech, the production of speech, which is how you control your speech articulators, and also maybe decode some like high-level planning about the speech. So that's why I want to put arrays into 2 different brain regions here. So the first thing we do after we put arrays in her brain is that we did some like a behavior test to see what kind of information we can decode from those arrays. So here's here's a result. That's the first result we got is that we're trying to classify different tasks here. The first plot is that we're trying to using these 4 arrays to classify the orofacial movements. So this dashed line is the cue that she's actually executing those orofacial movements. And then before this dashed line, she is trying to prefer to do those orofacial movements. So you can see that this 2 right line here show that you can predict those movements much better above chance using these 2 arrays in the motor cortex. Whereas these 2 arrays in the Broca's area, you can't really predict too much above chance, especially during the execution of those movements. And for single phonemes, which we instruct our participants to speak single English phonemes, you can also predict those things much higher above chance using these 2 arrays from the motor cortex, and also for the words, for single words, right? So what these results tell us is that for those 2 arrays we have put into T12's mind, these 2 arrays in the motor cortex contains a lot of information about the phonemes being articulated and also the words being articulated. But those 2 arrays in the Broca's area, which is supposed to help us to figure out the planning of the speech production, doesn't contain too much information. So that's really intriguing to us, and we're still trying to figure out why that's true. So for the rest of the talk here, we're mostly using only these 2 arrays in the motor cortex here. So now we know that there's phonetic information being encoded in those 2 arrays. What we're going to do next is actually trying to build a real-time brain-to-text PCI here. So what we're going to do is, let me just show you a video demo first to get a sense of what the BCA we're trying to build. So here, this is our participant. So she's connected to our decoding machine through this cable here, which transmits her neural signals in real time to a decoding machine. And then on the screen, you can see that there's a sentence there that we instructed her to copy, to basically to read aloud. And then once this red square turns green, she will try to speak. And then what you will see below here is what the machine is decoded.
I don't want to call her a babysitter. That would be good. I did well in school. I don't see much pollution turning on.
All right, so that's almost perfect decoding results from her. And you can tell from the video that although she can vocalize, but it's not really intelligible because of her limited artificial muscle movements. But we can still decode out from her brain signal that what she is trying to say. And this video is, so the task I just showed is she's trying to copy a sentence, but this is trying to answer a question here. And we also tried different modalities, which is because when she tries to attempting to articulate, it's actually very tiring for her to actually to articulate those sounds. So what we try here is that only instructed her to move her mouth or move her articulators, but not vocalize. So what we call this is silent speech, and we can still decode pretty well using this kind of silent speech modality.
I do not have much to compare it to. I don't read as much as I would like to either.
All right, okay. Okay, so let's just move on more technical details about how we build this speech BCI here. So, as I just mentioned, right, so the first thing we need to do is to try to build a decoder. And before building that decoder, we need to do some data collection. So here's our research scientist, Frank, sitting next to T12 and asking her to read that sentence on the screen. And then we'll record the neural activities of her saying that sentence. So we'll have this kind of a paired data, collected paired data, where the input is the neural activity and the output is the targeted sentence we want to decode. So we basically have to go to where T12 lived, and then we'll do some data collection session there, and then testing the decoder. The way we collect data is that because we only have very limited time, and we cannot ask her T12 to speak a lot of sentences, so we'll divide our data collection into this kind of like a block structure where we instructed her to speak 40 sentences every block, and then she take a break, and then we collect another block. So the data collection will last about 100 minutes for every research session. And then we'll train a decoder. Maybe that takes like 10 to 20 minutes. It's really quick. After training a decoder, we'll start actually evaluating the performance of the decoder by asking our participants to speak some new sentences and then see how well we can decode on those new set of sentences. So in total, we did the experiment sessions over maybe 3 months of time, and then we collect about like 10,000 sentences from this like a switchboard telephone conversation corpus which we really want to emphasize that we want to decode this kind of conversational English. Once we have the data, then we can try to see how we can design a decoder that can best solve this task. So let's first define the problem here. So we have some neural features inputs, right? So let's say we have some neural features, which is a time series. You can think about it as maybe similar to audio, that at each time point we'll get some feature vectors. The output of this decoder is a set of words, right? So we know that she's trying to speak some sentence, so we're trying to decode the words from this input neural features here. As I mentioned earlier, so instead of like directly decoding words from the input sentences, maybe we want to have this intermediate target of phonemes to decode. The reason is that first we know that there's only 40 phonemes in English, so that's a much smaller set compared to the number of words. So if you want to train a decoder that can actually decode words, then you need to have much more data to cover all the possible words. Whereas for phonemes, you probably need way less data to cover all the 40 phonemes here. So instead of directly decoding the words, we decided to decode an intermediate representation of phonemes from the neural input features. Okay, so basically there's two decoders we want to design. One is the first is a neural to phoneme decoder, and the second is a phoneme to word decoder. So that's the two decoders that we'll have to design this task. Let's focus on the neural to phoneme decoder first. So basically, I think at this point of class, we probably know that we can treat this problem as a sequence-to-sequence problem, right? So the input is some feature sequence, the output is a token sequence. And for sequence-to-sequence problem, we probably know that we can use some like encoder and decoder models to solve this problem, right? However, for encoder and decoder model, it's actually more powerful than we actually need, because encoder and decoder model allows this kind of arbitrary alignments between inputs and outputs. That's really helpful for tasks such as machine translation, whereas some languages has like different word orders than other languages. But here, we know that the alignment is kind of like a more monotonic compared to the say machine translation, where the alignment is arbitrary. By monotonic, I mean that that probably say for example the first two neural features probably corresponds to the first phonemes in the output sentence rather than the last phoneme in the output sentence, right? So this is kind of a monotonic alignment. So to solve this problems of monotonic alignments, we can actually borrow an idea that people have developed for machine learning tasks such as handwriting recognition and speech recognition, where the task is also trying to decode a ladder sequence or like phoneme sequence, and also ladder sequences from some speech features. And the technique you are going to use is called connectionist temporal classification. So for people who have taken CS224N, you probably already know what this means, but I'm going to do a little bit introduction about this thing. I guess I don't have too much time, but I just quickly go over it here. So what CTC, the connection temporal classification, do is that giving some input sequence, right? The goal is that we want to decode some output sequence, but we don't know the exact alignment between them. And usually the input and output has some length mismatch. For example, in the case of say speech recognition, where the input is have a length of several thousands of frames, right? So where each frame corresponds to a very fine level, fine high temporal resolution features such recorded at say 20 milliseconds, whereas the output only has a few tokens. So that's a huge length mismatch here. What we can do is we can still using say a RNN transformer model to predict what the output token is at each time step, right? And then we somehow have to figure out a way to fill in between the output tokens some spacers, so that the output token can also have the same length as the input output sequence can have the same length as the input sequence. So what the CTC loss does is introduce this additional blank token as output. With this blank token, what you can actually do is, for example, here is an example output of the CTC classifier. It's trying to produce this kind of like sequence here, right? What you can do is first you merge repeated tokens, and then you're taking out that blank tokens. So what you get is a much shorter sequence that corresponds to output. So what CTC loss does is it allows you to do a sequence problem that has a different input and output lengths, and also has this kind of monotonic alignment property. Let me just skip through this detail here, how you can train a CTC loss here. Just skip through this thing. So now let's suppose that we have this CTC loss that can actually be used to train our model, right? The next problem is what kind of decoder we want to use for this task. What kind of neural network decoders to use for this task? I think at this point of class, I think most of you guys are convinced that transformer is really powerful, right? There's no reason for me to say more about it. But in this case, we don't want to use transformer. The reason is that we don't have a large data set, as I mentioned previously. We only have 10,000 sentences, right? And also, transformer is really good at dealing with long-range dependencies. But here, for the speech production, there's no really required for long-range dependency. So let's just go back to the very simple RN. We know that RN works for small data sets, and it can predict, it can deal with short-range dependency pretty well. And another nice thing about RN is that it's very efficient to run in real time. You can do put a very complicated RN, even run it very efficiently on your mobile phone. The most popular RN we have learned is the LSTM, right? Uses this kind of like a memory state here. Where's my cursor? Use this memory state to trying to store some long-term, like long-range information, and then use this different input and forget gate, input and output gates to control how you can read and write into that memory state, right? But LSTM is also very complicated. There's a variant of LSTM called GRU, gated recurrent unit. It's I think the idea here is that just trying to combine this memory state and the hidden states into just one hidden state. By doing that, you can also reduce some gates. So GRU is basically a more simpler version of LSTM that works really well when you have a small data set. So here we use GRU instead of LSTM for our task. So now we know that how we can decode phonemes, and then we have neural network models to decode phonemes, right? We know how to train the model. So at inference time, by inference time, I mean that at testing time, you can pass in some neural activities into our decoders, and then you will decode out some like phoneme probabilities, right? So there's maybe at the first timestamp, the highest probability is high. The problem here is that how do I figure out the most likely output sequences giving this phoneme probabilities, right? So basically the task is to find the most likely output sequences here. I think for this problem, I think since we have already did something similar in the assignment 3, which is that we can use beam search to figure out the most likely sequence here. However, there's one caveat with the beam search when you're applying it to the CTC loss, but I'm not going to expand it too much here. Yeah, so let's just skip over that. Now suppose that we can use the beam search to find the most likely phoneme sequences. How do we convert that phoneme sequences into words, right? So that's because like we eventually want to decode sentences, but not just like a sequence of phonemes. So one thing you can modify the beam search is that you can, if you have like an English dictionary where you can map each word into its pronunciations, then while doing the beam search, we can basically see that if you decode some phoneme sequences that correspond to words, you can basically replace that phoneme sequence with that words, right? However, you can actually do better by using a language model. For example, here, that's the thing that's the decoding equation. What we want to do here is that here the x is the input, the y is the decoded the word sequences. And then because not all word sequences have the same likelihood, right? So some word sequences, say suppose I decode a sentence, say called I can spoke. That doesn't seem like a syntactically correct. So we can maybe use the language model to evaluate the probabilities of each decoded hypothesis, and then using that as some sort of weight on the final decoding probabilities. So we're adding this extra term here called the probabilities of sentence here. That's actually, you can just decompose that into the probabilities of each token giving its previous tokens. And you can basically measure these things using any language models, right? Now, another thing we want to add here is another term is the word insertion bonus. So one problem about this language model, this probability of sentence is that actually longer sentences will have smaller probabilities than shorter sentences. That's just like the properties of this, how you decompose that, this probability here. So we want to actually to balance the length of the decoded sequence here by adding some word insertion bonus. So what we are eventually trying to optimize is this equation here using both the probabilities generated by the RN decoder and then using some sort of language model like weights and then word insertion bonus. And also some weights here you can optimize. Okay, just trying to put everything together. So suppose that you have a neural feature inputs here, which is you get the neural features every 20 milliseconds. You pass that through a GRU and then you get some phoneme probabilities, right? This is all happens in real time, so everything has to happen under, like all computation needs to be done within 20 milliseconds. You do a really quick beam search and then you find, okay, maybe this phoneme corresponds to the word I or the word I. And then here we want to use the n-gram language model instead of like a more powerful transformer language model. The reason is that we want to really do a lot of like evaluation really quickly under 20 milliseconds. So suppose that you have like say 100 hypotheses, right? And then you want to all evaluate the possibility of them. If you use a transformer language model such as GPT-3, which is really powerful, but you cannot really like do really fast inferences under 20 milliseconds, right? So whereas the n-gram language model, you can just load everything into memory and all the evaluation is just a memory lookup, so it's really quick. After that, you can get some probabilities out and then you'll just keep, say, the top K hypothesis for the next step of a beam search here. So that's how we use the n-gram language model in the real-time decoding. After that, we'll use the transformer language model so to re-rank all the hypotheses generated by the n-gram language model. So this actually happens when you actually decode it out the entire sentence. Say, well, I can keep the most likely 100 sentences. And then at this time, I can use the transformer language model, which can quickly evaluate the probabilities, say only for 100 hypotheses under the time of maybe half a second, right? And then can get a better probability measurement of all the sentences here. Yeah, so putting everything together, this is how the entire system works. When I show you the previous video, is that we can right now using this complicated, not complicated, multi-stage machine learning model to accurately decode what the person is trying to say and build this high-performance neural speech BCI. All right, well, almost time here, so just skip the evaluation part. Evaluation is how we measure the performance. Is basically measured in the word error rate. You also have all the data open to as a competition. So if you guys are really curious about this thing, you can try to play around with it. I think here's I think the most exciting thing about doing this research is that you actually see how your research can impact people here. So this is a quote from our participant T12, and then this is how she reacts when this thing first worked for her. It's really exciting that she can speak after so many years of silence. Okay, so in the last 5 minutes, maybe I can just go a little bit into what I think is the future of BCIs here. So I think what I've just shown you guys is that using BCIs, we can help people to either restore movements or restore communication. One exciting direction, I think, is this kind of a multimodal BCI. Here is a work published by a group at UCSF, is that they are trying to decode not only the phonemes, but also speech, the actual speech, and then also some articulate gestures so that you can actually move 3D avatars here. And also, as I just mentioned, is that the final goal of the speech BCI is that you want to actually deploy it for people to be able to use it every day, just as we use our phones, right? So here's a more recent development of speech BCI by our collaborators at UC Davis. What they do is they actually put full arrays into the motor cortex, meaning that they can actually have better signals than we do. So what they can actually show you is that, so for here, just for reference, because I just forgot to mention that the final performance of our system is that we can get maybe around 25% word error. Means that for every 100 word, the participant says 25 of them maybe is wrong. So for this latest work at the UC Davis, they show that you can actually get close to 0 word error rate in a few sessions by training the system more and more continuously. So it's actually being very close to being actually a usable system right now. And here's a video of their participants using the system to type, to speak. It's very accurate. He's actually using the system to every day right now for communicating with his family and for work.
I really cannot be understated how important that is.
All right, so I think the most exciting direction I think happened, at least like personally I think is happening in our lab, is that we're trying to restore more effortless and natural communication by decoding this kind of inner speech. So previously, all the speech BCI I just show you, I think the maximum speed we can do is maybe decode at 60 to 70 words per minute, but that's still far slower compared to natural conversation, which happens at 150 words per minute. So one of the reasons is that for all these participants, if we ask them to trying to attempt to speak because they have been lost speech so many years, it's very hard for them to speak at a normal rate. However, we know that a lot of people have this kind of inner speech, right? We're kind of like talking to ourselves in our mind. I think the research question here is whether we can decode this sort of like an inner speech. So it is like some like a preliminary work from one collaborators in our lab shows that you can actually do so. So for example, here, the result shows that if you decode attempted speech, which is why I just show you that you can do maybe for a small set of words, you can do say at the 90% accuracy. But if you ask the participants to imagining moving her mouth or imagining like a voice in her head, you can do pretty well, right? So it's not as good as the attempted speech, but it's still much higher than chance. So I think this is showing that it's possible in the future that we can decode this sort of like an inner speech to fully restore like a natural communication to people like Howard and T12. But I think there's a more like controversial issue regarding this kind of inner speech, because what if like you can decode something that's your private thoughts or private memories that you don't want to express, right? That's a very difficult question here. And also, as I just mentioned, like not everyone has inner speech. And also someone maybe like when you think about this kind of like speech, right? Speech is just one external representation of your internal thoughts. It's just like a linear representation that you want to put out through this kind of like a medium of speech, whereas your inner thoughts could be more complex, more multidimensional. So it's very hard to decide where you want to put arrays and where you want to decode all of those inner thoughts. But I think that's also very exciting opportunities for us to learn more about like the speech processing in the brain. As I just mentioned, like if you want to decode this kind of inner speech, then you're also coming to this facing a lot of new ethical questions. That's really, I think, thought-provoking. For example, like suppose should we allow BCIs to decode or read their inner memories, right? Like, what if like we decode something you don't want to say, right? That's how can we deal with that? On the other hand, like, what if we can actually use these things to help people who has lost their memories due to like a Alzheimer's disease, right? Or we can read out some like subconscious fear that can help people to do their psychotherapies. Are this, like, how should we decide whether we want to allow this kind of inner thought decoding or not, or memory decoding or not? And also, I think a more like deeper question is like, what if like one day we could do this kind of like a cognitive enhancement with BCI, such as, what if you can move a robotic arm much faster than your real arm? Is that allowed? Or like, can you actually purchase a memory so that you can skip this CS224N class? Yeah, I think that's really a hard question to answer, but it's just like to throw this question out so that, we're not like, it's not like only a BCI problem, but we're also facing this problem right now, right? There's a lot of ways you can do enhancement on yourself. So I guess like what I'm trying to say here is that BCI will raise a lot of new ethical questions. So this is taking this quote from this textbook here. What it's trying to say is that I think this question is, we're not really looking for an answer here, but I think the point here is that maybe we just want to keep this in discussion with scientists, with engineers, with policymakers, and just to make sure that everything, we can use BCI to help people that really need them, and also be aware that there could be a lot of like potential issues here. I think just to give a summary here. So I think I hope I can convince you guys that BCI is a really cool new research directions. It's at the intersection of AI, machine learning, neuroscience, and neuroengineering. We'll soon have this kind of like systems that can really help people to be able to communicate again. And also there's a really cool opportunities to understand how the brain processes the languages. I think the most important thing is that we are bringing hope to people like Howard and T12. All right, thank you everyone. And special thanks to the people in my lab. Yeah.